Hey guys, welcome to a video about my blindfolded Pochmann Rubik's Cube solver. My name is Mridul Suresh and this video is about an application that I built to help people learn how to solve the Rubik's Cube blindfolded using the Pochmann method. I've always been fascinated by the Rubik's Cube and I first learned how to solve it when I was in grade 5. Since then, I've never forgotten, but I also never pushed the limits of what I could do. I've always been on and off with practicing speed cubing and I never really truly cared or felt interested in solving other Rubik's puzzles apart from the 3x3, even though I did learn a couple others. But one new thing definitely piqued my interest. I understand solving it with vision, but how is it even possible to solve a Rubik's Cube blindfolded? And so I learned. It doesn't use the same methods as regular solving, but it also doesn't take as much memorization as I first expected. While I was learning, I personally found it pretty difficult, whether that be assigning the right letters, or tracing the string I need to make, or even making the correct setup moves to get solving. I've looked online and I couldn't find any tool that helped with what I wanted or that could help accelerate the learning process efficiently. And so I thought, why not create one? I could definitely create some sort of application that could help throughout the learning process. One that I wish could have been there for me and one that I hope is there for others. Just before we get into the video, by the way, at each step in building the program, I'll explain at a pretty high level how solving with the blindfolded method using the Pochmann method actually works so that you kind of understand what the code actually does. To fully understand everything, or if you're just curious about how the blind solving method actually completely works, I've linked a video in the description that I actually personally use to help learn how to solve the Rubik's Cube blindfolded. And with that, let's get started. Actually, before we get into a part-by-part analysis, we'll quickly talk about the flow of the program without giving away too many spoilers. First, we want to show a scrambled cube to the camera. Then we want to track and display where each of the Pochmann letters would be. Then we want to generate the solving order strings for the edges and the corners. And finally, we want to generate the setup moves depending on the string solutions to solve the cube completely. So now let's actually move on to the application. So the first and foundational part for this program to work is accurate color classification. So we want to show a scrambled cube to the camera and we want to save a mapping of that cube so that we can use it later. I've used OpenCV, NumPy, scikit-learn, Python, and JSON. At first, I tried just manual color recognition by playing around with different HSV ranges. This didn't work as well as I wanted because lighting conditions can vary widely in different environments, not all stickers are uniform, and overall we don't get good generalization. So I decided to train an AI model. For all those reasons and just for fun. So now let's look at the actual code. So the way that the application starts is with the file capture.py. Capture.py simply uses the camera with an overlay of 9 grids to capture the face of the cube shown. Depending on the color you're showing to the camera, you can press that letter on your keyboard to capture all 9 stickers at once. So ideally, show a face of a solved cube and take a bunch of captures in different environments and lightings. This way, it's much faster and easier to capture training data, and especially based on your cube and environment. In the future, I do aim to fit the dataset with more cubes than just my own and more environments than my own, but for now, this is just the simplest workflow. Next, we have train.py. Train.py reads the dataset of the sticker images, computes the HSV color for each one, trains a KNN model, creates HSV label map.json, and creates HSV KNN model.joblib, which stores the trained model. .joblib is a file-saved version of a Python object. So this can include ML models, large datasets, feature transformers, and more. So in our case, it stores the KNN model trained on our dataset. One important thing that we'll talk shortly about is why I chose to train a KNN over any other model. The final file that we have is predict.py. This is used just for fun as a sanity check to play around and test the trained model to see how it performs predicting the colors on the face shown. Feel free to play around with this and definitely show a scrambled cube to the camera. So now let's discuss why I chose to train a KNN. It's a lot to talk about and it doesn't have anything to specifically do with the app, so I'll put it up on the screen and you can feel free to pause and read if you'd like. So why did I choose to train a KNN over a CNN? Well, I actually tried a CNN first, and here's what I learned. So it's important to not just pick the fanciest model, but rather to pick the one that best matches the problem at hand. Now, constant sticker tracking and identification is not implemented in this project. The reason being that labeling huge amounts of stickers for what I would gain is not really worth it. The main improvement would be, instead of tightly focusing your cube on a predetermined 3x3 grid, you'd have some leniency or tolerance towards how loosely you can show it. I initially planned on using label image to label a high quality dataset of images to train a YOLO v5 model on, but quickly decided against it in order to keep the project moving along. And also because too much time would be spent on a minor improvement. Optionally, and as a highly reasonable idea, I could use a public dataset from something like RoboFlow or directly even just use an open source project that detects stickers and their colors with a high quality labeled dataset and a pre-trained model, but where's the fun in that? There are a couple important things that I did learn here though. So this part of the project was a whole lot of trial and error and a whole lot of learning. But that's part of the process, isn't it? Now comes the most important part of blind solving, that is letter classification and memorization. It's not necessarily difficult, it just takes some getting used to and a whole lot of practice. It's important to now start talking about how the Pochmann method actually works so that you understand what the code does. So on each face, you have 4 letters arranged alphabetically in clockwise order. You go top face, left face, front face, right face, back face, and finally bottom. Of course, it doesn't actually matter how you choose to letter them as long as you have some consistent method, but this is just how I learned and I believe it's the most popular. Also note that throughout this lettering scheme and throughout my application, the way that the cube is being shown to the camera is standard, with the green face being the front and the white face being the top. Now, remembering which letters go where takes time. So an important part of my application is actually the letter classification. So in the letter classification folder, we have 5 files. In the workflow, the first file is mapper.py. Mapper.py loads the KNN model that we've trained with high confidence to map the entire cube into a 2D state. The file opens up the camera and instructs the user on how the cube should be held during the capture of each of the 6 faces. It's very important for the model to perform accurately here, or else our mapping of the cube will be incorrect. Of course, if even a single color is classified incorrectly, it can be manually changed instead of rescanning the entire cube again. Mapper.py saves the scrambled cube to scramblecube.json, which of course can be manually edited in the case of any inaccuracies. The mapping is stored as a dictionary or map. Each face has its corresponding relative side of the face, with F being front, U being up, B being back, and so on. Mapper.py also creates another important file, which is scrambledrotations.json. At the end of the mapper script that captures the cube, a function is called to generate rotations of each of the 6 faces, rotated through 0, 90, 180, and 270 degrees, and store them in scrambledrotations.json. So we end up with another dictionary with 4 keys for each face, being the face position and the letter, such as F1 being the green face with white on top, and F3 being the green face with yellow on top, which is just the white face rotated 180 degrees. Then we have a third file, but this one's hard-coded. This is mapping.json, and it just maps the face and orientation to how the letters would be shown. You can see we're just mapping the according letters shifted right, which is clockwise, to match the orientation of the face. And finally, we have the file that brings it all together, lettering.py. When lettering.py is run, the first thing is that the camera with our classic grid opens up. Now when space is clicked, we again use our trained KNN to predict all the 9 colors of the cube's face being shown to the camera. What's important here is that we compare the predicted face to all of the faces stored in scrambledrotations.json. If 7 out of 9 or more match, we take that face as the face being shown and we print the face that's being shown, like U3 in the terminal for example. We then take that face and check mapping.json for the correct orientation of the letters, and there we go. We can see the letters of both the edges and the corners on the screen. So the ideal usage is, as you're figuring out where each letter should be placed, if at any time you want to recall the letter of a specific piece, instead of going through the alphabet and tracing until that letter, you just hold it up to the camera, click space, and you already know what letter that piece is supposed to be. This way, you also have no way of making a mistake and mislettering a piece while trying to commit it to memory, which is a frustrating mistake that I've unfortunately made many times. Before we continue, I think it's important to talk about something. So a whole lot of what I've done, I'd actually have no idea how to do before. And so a huge helping hand in that was generative AI, whether that be, Cursor, Claude, GPT, whatever. When building intricate programs, system design still comes down to the engineer. Trying to use AI to one-shot huge parts of a program is extremely unrealistic, and it doesn't even work for a project like this. It's important to think about how you want to design your solution before you even open up an LLM. Breaking down the solution into smaller manageable parts that fit into one big puzzle is what really works. Of course, the tempting thing to do is throw in as much context as you can and try to get it to one-shot your solution, but it doesn't often work. And if it did, I think there's a bigger issue at hand. So now we get to the core of the application, the actual string generation used for solving the cube. This part actually has no aid from AI. It simply fails to understand the actual goal and fails to visualize what the process is supposed to look like, no matter how much context you try dumping. I guess cursor recommendations for the hardcore static mappings were used, but does that really even count? That only saves time, and is all quadruple checked anyways since it needs to be flawless for the app to actually work. So now how is solving the cube blindfolded actually done? We've already talked about the lettering scheme, so how do we actually put this into use? Now we can look at how this is implemented in the application. We can see in the folder string generation, there are 2 files, which are generatestrings.py and cubesolutionorder.json. In generatestring.py, first we access the scramble JSON from letter classification. The first half of the file is for edge solving and the second half is for corners. Starting with edges, we have a list called solved that will contain all of the letters that are already solved. Notice how the buffer letters start in solved, as technically we never solved the buffer directly. We then have order, which will contain the final order and a list of the letters being used. Then we have a static mapping of edge pieces and their letters, and a static mapping of letters to the locations on the current cube state. Our first function is find already solved, which takes cube and locations. It's just a bunch of standard hard-coded if conditions for all 12 edge pieces to see which are already solved, so that we don't interfere with the solved pieces. Next is another hard-coded dictionary called correspondence. which maps each letter to the other letter of the same edge piece, since each edge piece consists of 2 faces. Now for the main part, we start C1 and C2, which are short for color, at the buffer. We know the piece and letter to start on now. In our loop, if the number of unique elements solved is 24, we know we're done. If the letter we're currently tracing isn't marked or it isn't the buffer, we add the letter to the order, add the letter to solve, and add its corresponding letter to solved as well, since we're solving the entire edge piece that consists of both faces. We then trace the next piece and letter and continue on. If the next piece is the buffer, we know we have to pick a random unsolved piece. So this is done using a simple for loop through letters, and we also set temp flag to true. That way, when we hit the main part of the loop, we can remove the correspondence letter from the solved, since we'll need to loop back and solve it after the cycle we're tracing. We also set it as marked so that we know that when we come back to that piece, we know a cycle is finished and that we need to choose a new piece again, like how we do for if it was the buffer. Then we have corners. We can see the buffer is the AER piece and it starts in solve. If the number of letters in the generated solution for edges is odd, it means that 2 corners have been swapped, but we'll deal with this later. We then have corner mapping, corner location mapping, finding already solved corners, and a 3-way correspondence for each letter. The rest of the code remains pretty much the same as edges, but adapted to work for corner pieces. And so finally, we end with an output like this, which is actually the exact solution to this scramble and exactly what we're looking for. These solutions are then saved to cube solution order.json. Now we're actually ready to apply algorithms and solve the cube. Now let's talk about the last step, actually moving the cube to solve it. In the folder move generation, we have a single file called solvingmoves.py. In this file, we load the correct orders that we've calculated using generatestrings.py. We then have 4 static mappings of each edge and corner letter to the moves required to set up that piece, and also its reverse moves. Note that the reverse isn't just the reverse of the order, but it's actually the opposite move. We then simply take each letter in the order for edges and print the corresponding moves to set up the piece, print that we need to do our swapping algorithm, which is the tperm, and then also the reverse moves to put our solved piece right back in the right place. We then check for parity and print the algorithm if required, and follow the same steps for edges but for corners. Overall, a pretty simple file. But after this file, the entire Rubik's Cube should be completely solved by using the blindfolded Old Pochmann method. Obviously, there are a bunch of improvements that could be made to the application. This is just the core functionality without any added visual or user experience fluff. I'd love to make a deployed version of this app with improved user experience, but at least the core functionality is out there right now for you guys to use. So overall, this was an immensely fun and challenging project. I definitely learned a lot throughout making this project, and I love solving a problem by creating a project that's never been done before. I hope that you guys find this application useful and that you guys love it as much as I do. Feel free to check it out on GitHub and don't hesitate to reach out about anything at all. Thank you guys so much for watching. My name is Manolo Suresh and I'll see you guys next time.